In the last lesson, we looked at the electrophilic aromatic substitution mechanism by which a nitro group can be introduced on an aromatic ring. In this lesson, we're going to discuss the synthetic utility of introducing this nitro group and discuss the wide variety of substituted benzenes that can be prepared. The synthetic sequence that allows new substitution on an aromatic ring is first by nitrating the group and introducing a nitro group, and then reducing this nitro group to an aniline. This aniline is then converted into an Arenediazonium compound. It is this Arenediazonium compound that allows access to many different substituted benzenes when it is treated with a nucleophile in a substitution reaction. This overall synthetic sequence is probably the single most versatile method of aromatic substitution, and we'll elaborate on it in the next few slides. But first, let's look at how we convert this nitro group to an amine. The nitro-substituted benzene can be reduced to an aniline by treatment with either a tin reagent and hydrochloric acid or a hydrogenation catalyst such as palladium on carbon under an atmosphere of hydrogen. Both reactions can be utilized to reduce the nitro group, and as is common in organic chemistry, it is often compound specific as to which reaction conditions are chosen. Now that we have the aniline in hand, let's take a look at the synthetic utility this opens up for us. The aniline can be converted to the Arenediazonium salt by treatment with sodium nitrite and an acid source, keeping the reaction temperature between 0 and 5 degrees Celsius. As you can see, the Arenediazonium compound can provide access to many substituted benzenes. It's not important to memorize each reaction and set of reagents, but what is important is to understand the significance of the Arenediazonium ion and recognize its synthetic usefulness. Let's take a look at the mechanism of the formation of the diazonium compound. Remember, we have sodium nitrite, an acid source, and aniline as our starting materials for this reaction. First, protonation of the nitrite yields nitrous acid. Water is then eliminated to yield the nitrosonium ion or the nitrosyl cation. Aniline then enters into the mechanism by nucleophilic attack. Comparing this intermediate with the product, you can see the atoms that need to be removed to reach our target. A series of proton transfer steps sets up this intermediate to eliminate water in a beta elimination step to yield the diazonium ion. It's important to note that this reaction must be carried out at 0 degrees Celsius because the diazonium ion is unstable at higher temperatures. Also, I would suggest taking this mechanism and practice pushing the arrows for each step. You can never have enough practice in pushing electrons. However, let's push forward with the diazonium salt and look at the general mechanistic pathway that this compound undergoes to access all the substituted benzenes we saw in the last slide. The general pathway that the diazonium ion undergoes is shown in this two-step process. The loss of molecular nitrogen drives this process, as the aryl cation that is formed can react with a variety of nucleophiles, which makes this a versatile method to introduce substitution on an aromatic ring. Remember though that this is fundamentally different than the electrophilic aromatic substitution mechanism, because in this case the aromatic ring is acting as an electrophile and not a nucleophile. In this webcast we connected our knowledge of the nitration of an aromatic ring and how we can reduce that nitro group to an amine. The amine can then be converted to a diazonium ion, which allows access to a wide variety of substituted benzenes.